Oh, hey everybody. I'm eating some cashews. They're seasoned with sea salt. Anyhow, I have a little bit of anxiety, and I read that cashews help you uptake magnesium. Anyhow, that's magnesium right there. It's metal. So while eating these cashews, I'm actually eating little hunks of metal. All right. Nice talk, guys. I'll see you later. Actually, I should probably state what's really going on. That's not magnesium, metal in these. This is ionic magnesium. It's magnesium ion. And when the doctor tells me I shouldn't eat the salted ones, even though I do, that's sodium ion. It's not the metal sodium. It's not the metal magnesium in cashews, or helping you uptake magnesium or whatever, I don't know. So let's talk about ions and stable ions and one of the most important concepts, the Octet Rule, right now. Well, howdy everybody, howdy. Mike here again to talk to you about what is really, and I'm not overstating this, I'm not overselling it. Today is going to be one of the most important lessons for you. If you can really just sort of latch on to this material today, put it deep in your brain, it's going to come back over and over and over again, and it will be your best friend. And that is the concept of what's stable and what's not is dictated by a thing called the Octet Rule. But first, let's talk about atoms some more. So I don't think, given what we've talked about, that what I'm going to do is I'm going to talk about potassium. Now, potassium's what's in a banana, right? Got a banana right here. But the problem is potassium as an atom is not stable. Let me say that again. Potassium, the atom, is not stable. And now the reason is from the thing called the Octet Rule. But I'll say when your doctor is saying, or your nutritionist or whatever, is saying potassium needs to be in your diet and you need to eat almonds or bananas or whatever, that is called potassium ion. Now, that is K+. Potassium metal, I almost want you to think of it as it's a metal. And by the way, we're going to get into the periodic table later. It's right there in the periodic table. Potassium, K. Think of that as almost like having a zero here. That plus over there is a charge. Now when we have a zero, it's understood that if nothing's there, it's a zero. So when you see K just by itself, that means there's equal number of protons and electrons, and that thing has a net charge of 0. Now let's talk about why K+ is potassium ion. And I think I told you that everything in the nucleus is buried down in there. Nothing going to change with that. That's a charge of plus 19. What has happened is the atom potassium becomes potassium ion because it has lost an electron. So the charge here is plus 1. So think of it going from here to there, it would have to lose an electron. Now this is very tricky for some folks, so it's going to take some practice on your part. That plus doesn't mean it gains something. It's actually lost, if anything, an electron. But electrons are negative, so if there's more protons than electrons, an atom will stop becoming an ion, and it will stop becoming an atom and become an ion. And so it happens to be that this is unstable, excuse me. As a matter of fact, if you put potassium in water, the metal, it will make, it'll get hot, it'll emit hydrogen, and the hydrogen will catch on fire. Here's a photo of that. Now, much to the contrary, potassium ion is what's inside you, and that is a stable form of potassium. And now, just to demonstrate, I'm going to take this banana. Here's some water. I'm going to take, this is what we call in science a bowl of water. Here's a banana. I'm going to take a piece of that banana. Now watch, hold on, stand back. Oh, that's what we call in science nothing. Because the potassium in the banana is stable, it won't go through a chemical change. It doesn't need to necessarily, and that's because that form of potassium is stable as it is. Let's talk about some more ions. You may have been told to not have too much sodium in your diet. Let's take a look right there. Sodium. This is a package of ramen noodles because I'm making that kind of money. This is a package of ramen noodles, says 700 milligrams. That's almost a gram. That's a lot of sodium. But the sodium is not Na0. That would have 11. You have to go look up the atomic number, right? You go look up in the periodic table, atomic number 11, 11 protons, 11 electrons, overall charge is 0. Not stable. The stable form of sodium is called sodium ion. That would have the 11 protons still. So you see the pattern that's going on here? All the action is in the electrons. Lost or gained, that's what's causing most chemical changes, is loss and gain of electrons, or action in the electrons that's like that. So you might ask, well, why don't they just call it sodium ion? Well, you know what we do in society is we truncate things. And then if you use the word ion with somebody on the street, they would think that's some sort of Saturn car, you know. So this is magnesium metal. And I mentioned that needs to be in your diet in a much smaller amount than sodium. But nonetheless, what happens here is that the stable form of magnesium is not necessarily the metal. As a matter of fact, if you ground that piece of magnesium up, and make it into a powder, it would very easily catch on fire and make very, very bright white light. That's what's in fireworks. Magnesium, look it up in it's the neighbor of sodium. So in the periodic table, that's atomic number of 12. That would be magnesium metal, 12 protons, 12 electrons. The stable form of magnesium is magnesium ion. And that's in your drinking water. It's not going to hurt you. It's actually good for you. Notice 12 protons, 10 electrons. And that is stable. And I think I want to point out here, being that this form of sodium is stable. This form of magnesium is stable. Notice 10 electrons. 10 electrons. Yeah, it has a positive 2 charge. So there are certain stopping points where if an atom or an ion has a certain number of electrons, it becomes stable. We're going to define that as later on called the Octet Rule. You might use toothpaste, if you believe in that kind of thing, that has fluoride in it. That's fluorine, the atom, 9 protons, 9 electrons. That was one of the first examples we did. What's the stable form of fluorine is fluoride ion. 10 electrons. Wow, what do you know? 10 electrons again. It happened 3 times in a row. And that would be positive 9 for the 9 protons, and negative 10 equals minus 1. And so the charges of ions can vary, but you notice that there's certain stopping points of numbers of electrons that are stable. And actually, that's what we're going to talk about next, and I want you to really get ready for one of the very, very important patterns. I guess you'd call it a rule. It sounds kind of boring when you call it a rule, but one of the most significant patterns of this chemistry course, and we will talk about it months and months from now. And if you take it for the whole year, and if you take organic chemistry, it's a very important thing called the Octet Rule. Let's define the Octet Rule next. There it is, folks. In all its glory, it's pretty simple. The Octet Rule says that an atom or ion is most stable when it has the same number of electrons as a noble gas atom. So let's go take those examples we were talking about. There were 3 of them with 10 electrons. So we had sodium plus 1. Then we had magnesium 2+, and we had fluoride ion. Guess what? Those all have 10 electrons, and this family in the periodic table. Now let's talk about the periodic table. You have what we call families in the vertical columns. And sometimes they have cute names, like these are all called the alkali metals, and these are called the alkaline earth metals. And with fluoride, they're called the halogens. These are called the noble gases. So the last column in the periodic table, if an atom is close to that column, like say fluorine, it's not going to be as stable as it could be unless it could gain another electron and become 10 electrons like, but not, it is not neon, but it is like neon in the structure of its electrons, which, by the way, neon atomic number 10 is stable as an atom. And that's why they call them the noble gas atoms, because noble means unreactive. Now, if something already obeys the Octet Rule, it's got nowhere to go. It doesn't have to do a thing. It already obeys the Octet Rule. So all of the noble gas atoms obey the Octet Rule. All the other atoms have some work to do in terms of gaining or losing electrons. Now, I just want to say this. You could ask me, why does this exist? And I can say with all brutal honesty, I don't know. I don't know. I don't know if anybody knows for sure, but you could do this, folks. Here's a pen, all right? That's what we call in science a pen. I'm going to drop it, all right? Why'd that happen? Why'd that happen? Oh, because, well, the pen has mass and the earth has mass and they have a force that attracts each other. Why? Because, 9.8 meters per second squared. Why? You're only like 3 Y's away from not knowing the answer at any particular time. So don't try to understand why. It just is. Just like gravity, we don't understand why gravity. So this is just a pattern that happens. And now I'm going to talk a little bit more about the periodic table here, because what I don't like about the more modern version of the periodic table is that it's numbered 1 through 18. And I don't like that, because there's a region of the periodic table that really applies the Octet Rule really well. The Octet Rule applies to it really well. And there are regions where it doesn't. So the Octet Rule has a kind of tough part applying itself in this middle part called the transition metals. That's these columns. So for example, you'll notice that iron has about 3 different forms. They're all important to be different. There's iron. That's iron 0. That's the metal. But there's iron 2+ in your hemoglobin, and there's iron 3+ when iron rusts. So there's multiple things, and you'll notice that in the transition metals, they're so far away from the noble gases that they kind of find their own rule. This is called the main group. Here to there, and here. Here. What I like is if you look at an old periodic table, it'll split these into B, so this would be 1B, 2B, 3B, etc. And A, so they'll call this 1A, 2A. And then we'll skip the transition metals because it doesn't quite apply. The octet rule doesn't quite apply as well. And then what they'll do is, instead of numbering it 1 through 18 like the whole thing is, everything's the same, they'll say 3A, 4A, 5A, 6A, 7A, 8A. And frankly, folks, I would like if you did that to your periodic table. If you got one on paper, don't do it to the one in your book necessarily. But what you've got now is a pattern for which ions are stable and which are not. I don't know, but here's the thing. Memorizing rules or patterns, it's more bulletproof if you memorize the foundation, which is below that rule or pattern, which is that all these atoms are trying to gain or lose electrons until they have the same number of electrons. So you see where these are too far away and they can't really obey the octet rule. These are 1 electron away and they got to gain. See, if fluorine with 9, let's go chlorine with 17, were to gain 1 more electron, it would have 18, it would obey the octet rule, and that's Cl minus, because electrons are negative. So negative 1s, negative 2s, negative 3s, too much in the middle does nothing. We'll talk about what happens there. This would have to lose an electron, lose an electron. You got to watch out, actually here, this staircase is where the metals start and end. That's where metals are divided. And while we're at it, let's talk about these are called groups or families. That's the vertical columns. And so you see why they call it the periodic table. Everything in this family is going to make a +1 ion. Everything in this family is going to make a +2. So we were talking about magnesium. Well, calcium's in the same family as magnesium, and when we say, hey, you need some calcium in your diet, they're not talking about calcium metal, they're talking about calcium ion. And so, okay, let's say that you like to follow rules. You like some nice tidy rules to hopefully not memorize. I tend to be very, this would be patterns of ion formation. And this applies only to the main group. 1 through 8A. Metals. Group number is the charge. So let's go over here to the alkali metals group 1A. And you got lithium makes a +1 because it's got 3 electrons, and it would have to lose an electron to be like helium, which is 2 electrons. And we got done talking about sodium would be 10 electrons, which has the same number of electrons as neon. And you got potassium, which would have 18 electrons just like argon. And if you went further down, now we're starting to get into things that are a little bit more obscure, but rubidium would have 36 electrons just like krypton. So we go over to group 2A, and then we got beryllium. And then we got, next to sodium, we got magnesium, calcium, right? And then under that, we got strontium. See why they call it the periodic table? It repeats itself. And these things would be called periods. Periods 1, 2, that's the horizontal columns. Horizontal columns, horizontal rows. Okay, skip the transition metals. Now we're running out of metals, and there's just like aluminum would have 10 electrons, just like everything else that's in that same period that's a metal, like sodium, magnesium. I drew it up a little high. It's in the same row. So you see that? And that's how it is. You could say, hey, does magnesium ever make a +1? No, not stable. Does it make a +3? No. It stops at the sweet spot. Once again, you don't have to know why. All right? It just is. It's just a thing of the universe. It's a mystery. Non-metals, here's where 8 comes in. Group number -8, like octet. So we talked about fluoride, same as neon. And then we go down to chloride, same as argon. And then we go down to bromide, same as krypton. This would be 10 electrons. This would be 18 electrons. This would be 36 electrons. See the pattern? It's not that hard. Go over 1. Oxygen makes a -2. And sulfur makes sulfide, -2. Let's try to maintain sort of normalcy here. Let's stay up high on the periodic table to the common things that touch your life. Nitride, phosphide. This is group number 5A. 5 minus 8, -3. Now you go over here and say, hey, carbon, that's 4A. 4 minus, is it going to do this? Is it going to do 4 plus or 4 minus? And to be honest with you, when you get over to carbon's family, now we're getting to the point where 4 electrons, nature's starting to say that's a little bit too much work. We're going to find something else. We're going to share electrons and not transfer. And that's how we're going to obey the octet rule. And that's going to be a good old 3-week discussion later in the course. So really deep stuff there. So you find out when you're in group 4, you're kind of in the middle and it does nothing. Kind of like the period, it's got to find its own path. But when you're 1, 2, 3 electrons away, there's going to be loss or gain of electrons. And so now here's what's coming next. And I've dumped a lot on you today, folks. And so I'm going to say, hey, I'm going to make what happens when a sodium ion and a chloride ion meet up with each other. Well, what about opposites, right? Opposite charges. Opposites attract. It ain't fiction. It's a natural fact. That Paula Abdul wrote those words. But what you find out is that they're going to make a compound, sodium chloride, just like good old table salt, right? That's sodium chloride. What if magnesium and chloride meet up with each other? Uh-oh, we don't have this equal number of charges. They got to have equal number of loss and gain. Somebody can't obey the octet rule here unless, of course, we add another chloride. So there's certain proportions that have to occur with some kinds of compounds. The way that everybody can get what they need is if magnesium loses the 2 electrons and it goes, each of the electrons go to a chloride. And so next time we are going to have formula boot camp. If it's a metal and a non-metal, its formula is very predictable, and those are what we call ionic compounds or salts. But folks, you have just basically experienced a concept which is going to have a great deal of recall in this course. So recite this thing to yourself all day long, and then use examples. But see, there's not, everybody, I don't know why people are scared of chemistry, and it's because sometimes people say, go memorize this whole thing. You don't have to memorize anything on this thing. You know, we got names on there. You just got to know which column or which family something occurs in the periodic table. It looks intimidating if you look at it all. There's numbers or symbols or da-da-da. But there's patterns to it. And those patterns that are important are namely the vertical columns and what they will do if they can become like noble gases in terms of their electrons, because electrons are the only things that can move around, folks. Protons, neutrons, they're locked in there in that little blueberry-sized thing we call the nucleus, but it's tightly bound. You start doing something to the nucleus, oh, now we're doing splitting atoms, and that's a different ball game. But what happens passively when I put a piece of potassium metal into water, that's just nature going the way it wants to go. Okay, folks, try to get that solidified into your brain. Very important, the octet rule, because we're going to talk about it more next time. We'll see you then. Ciao.